So today I'm going to talk about the counterexample to Hedetniemi's conjecture. This breakthrough result obtained by Shitov. So let's first explain what is the conjecture. The conjecture is about the commutative product of graphs. Suppose G is a graph and H is a graph. The product, the graph has vertices, the pairs x, y. X is a vertex of G and y is a vertex of H, in which x, y is adjacent to x prime, y prime, if and only if x is adjacent to x prime in G and y is adjacent to y prime in H. Now, if you have a k-coloring, if phi is a proper k-coloring, it's a proper k-coloring of G, then it leads up to a proper k-coloring of the product graph. Then this is xy equals phi x. This is a proper k-coloring of the product graph of G times H. So this shows that the commutative of the product of is bounded by the commutative of G, and similarly is bounded by the commutative of H. So therefore, the commutative of G times H is less or equal to the minimum of the commutative of G and the commutative of H. Now, Hedetniemi conjecture, it conjectures that this equality always holds. This is Hedetniemi conjecture. That is for every graph G and H, the commutative of the product of G and H equals the minimum of G and H, commutative of G and H. So this conjecture was proposed in 1966. It's more than half century ago, and it received a lot of attention, but there was not much progress. It is known that if the minimum of these two, the commutative is at most 4, then it is true. And it is known that, but it is otherwise it's open. There's some other special cases approved. So last year, Shitov disproved this conjecture. It's 2019. Just this conjecture is not true, the conjecture is not true, it's false. That means there exists a graph G and the graph H, the commutative of the product is strictly less than the minimum of the commutative of G and H. Okay, so I'm going to show this proof. To prove this result, we need to construct a graph. Just construct a graph in the G and H. So the construction is by using the tool called exponential graph. Okay, first I need to define what is the exponential graph. Exponential graph. Suppose C is an integer, positive integer, and G is a graph. So this is the KC, you can think this is a complete graph to the power of G. This is the exponential graph. So what is this graph? The vertices are those maps find from vertex of G to this C. This means that 1 to C. So this is set. So you can think of the vertices of this graph are all the colorings of vertices of G by same colors. But this colorings need not to be proper. It's an arbitrary colorings of the vertices of G by same colors. Now when two maps, so you have two maps, that means that the two maps from here, the two vertices of this graph, they are adjacent if and only if for every edge, this is for every edge in G, phi x is different from the side 1. So this is the vertex, and this defines the edges. So this defines the exponential graph. In particular, you can start this. In particular, if phi is adjacent to phi, it's a loop in this graph. If and only if phi is proper current, right? Is proper. So that means for every edge, phi x is different from phi y. So it's a proper current. Another observation is that it's important is because phi and all the vertices of this graph, I will call it maps, okay? Because it's a map from G to Kc, because there are too many graphs involved. So I call vertices of this graph is a map. It's actually a map. So another observation is that if the image of phi is disjoint from the image of the sign, then these two are adjacent, right? This is certainly true for every edge. They assign different colors to the end vertices. Okay, so there's a set of particular mappings that are very important. So for I belongs to C, the GI is, we use GI to denote this map. This is the map with image set GI equals R, which means that it's a constant map. I said each vertex up here is a coloring of the vertex of G by colors from C. And the GI means that color all the vertices by same color, that is color I. Okay. Now then, this family, say this I belongs to C. Say this, for different colors from C, GI and GGI, they're adjacent because their image is disjoint. So this pairwise adjacent, this is set of maps of pairwise adjacent. So this induces a copy of Kc. Okay. It's a complete graph of Kc. Okay. Another important observation, so use this sign in an observation. Another important observation is that for every G, for every C, any G, any color, any integer, any graph, any integer. So this graph, G times KCG, this graph has a Banach number at the most C. Okay. That's a simple proof. It's right, a simple proof, because I want to color this product graph, so I just assign color to the product graph. The product graph has, so this is a vertex of G, and this is a map from this vertex here, that's a map, and this is one vertex. I just assign color phi v. Okay? And this is a proper current. This is a proper safe current. It's easy to verify it. Okay, so then if you want to disprove Hedetniemi conjecture, what you need to do, so that's what the Shitov did, is that so find the graph G and integer c such that the chromatic number of this graph is bigger than c, and also the chromatic number of this exponential graph is bigger than c. If you can do this, then you are done. You disprove this conjecture. Okay? Because both graphs has chromatic number bigger than c, but their product is chromatic number at most c. So that therefore the product graph, the chromatic number is strictly less than the minimum of these two. Okay, so this is exactly what Shitov did, and actually we're going to construct this graph. What are the so for this we need just to construct one graph and find one integer. Okay, so we're going to construct this graph. So this graph is as follows. Okay. Assume G is a graph. Assume G is a graph with p vertices and his girth is at least 6, and the independence number, so the maximum independent, the size of maximum independent set is less or equal to p over 4.1, and so about less than a quarter of the vertices form independent set. So assume you have such a graph. The existence of such a graph is all known. It is its result in every textbook, almost every textbook in graph theory, which is proved by Hedetniemi by using probability method. The result is usually say like this graph of arbitrary logical and arbitrary chromatic number. In the proof, this result is proved there. Okay, so I have such a graph. Then let q be any integer which is greater or equal to 2 to the p minus 1 times p squared, and c equals 4q plus 2. So this is given. Then what happens is that if this is the graph and this is the integer chosen like this, then we have the following conclusion. Then the chromatic number of GKQ, this is the next co-graph product of G and KQ, is greater than C, and the chromatic number of KCGKQ is also greater than C. So once this is proved, then we are done. So we have one graph. So one graph, the chromatic number is bigger than C, and Kc to the power of that graph is also bigger than C. Then their product as chromatic number most C. Okay. So what is GKQ? Say GKQ. That's GKQ. Just blow up each vertex of G into a clique of size Q. Okay. It's blow up each vertex of G to a copy of KQ. Okay. So the vertices, with the vertices of this graph, the vertices of this graph will be written as pairs V and I. V is a vertex of G, and I is integer in this set Q. And VI is adjacent to UJ if and only if either U is adjacent to V or U is equal to V and I is not J. So if you look at a single vertex V, then I goes to all the integers Q, you got a copy of KQ. If U and V are adjacent, they complete adjacent between these two copies of KQ. So this is the lexical product of these two graphs. Okay, so we're going to prove this theorem. So once this is proved, then we are done. Okay. So we have to prove this, the Comac number of this graph is bigger than C, and the Comac number of this graph is bigger than C. Okay. So the first one is trivial. So what is the Comac number of this one? Which is greater or equal to the number of vertices. The number of vertices P times Q, because G has P vertices, and each vertex is blowing up in the Q clique, so it has that many vertices. And this is divided by the independence number of this graph. Right? Because each color class is going to be independent set, and therefore each color class contains at most these many vertices. So you need at least that many colors. So the Comac number is at least this big. But the independence number of this graph, you blow up each vertex of G into a clique, and the independence number does not change. So it is still alpha G. And we know that alpha G, by our assumption, alpha G is bounded by P of 4.1. So it's P of 4.1. And this is 4.1 Q, which is bigger than 4Q plus 2. Okay? Q is huge number. P is in here. P is it's about 200. I'm not quite sure, but it's about 200. But Q is huge. Right? Q is something like 2 to the 200, huge number. And 0 times Q is certainly bigger than 2. So this is C. Right? This is C. So this Comac number of this graph is bigger than C. That is easy part. Okay? This one is easy. Now, so what we need to prove is prove that the exponential graph has Comac number bigger than C. For that purpose, we assume that we have a coloring. It's a C color. It's a C coloring of the exponential graph of K, C, G, K, Q. Okay. We're going to derive a contradiction. Suppose there's a C coloring, we're going to derive a contradiction. Remember that GI, say this GI, that's constant map, colors all the vertices by color I. Then form a clique, C clique. So this is a C coloring, and there's a C clique in there. So this C clique, we can. So this is a clique, right? C is a C clique. It is a C clique. So we can assume that they're colored by. They must be colored by distinct colors. So we can assume this is. This is the coloring. This is the sign. We use sign to note this coloring. So this is I. We can assume this is I. Maybe I write a 5. This is easier to write a 5. Something not use. And use this 5. Okay. Okay. So then. There's another observation is that for every map belongs corresponds to this KC, GKQ, every vertex of this exponential graph. The color is in the image. The color of this map is in the image. This is true. Let's write the proof here. This is true. Say if I is not in the image, if I is not in the image of phi, then phi is adjacent to GI, right? Because the image of GI is I, and I is not in the image, so it's adjacent, and therefore this phi has to be different. From the color of GI, which is I, right? So I is not a color. So the color of each map has to be in the image. Okay. Now, we define simple map. A simple map to be so a map phi in here is called simple. I call it simple. It's simple. I call it simple if they assign to all the copies of KQ the same color. This is what phi vi equals phi v j for every v in the G and for every I j in Q. So GKQ is by blow up each vertex of G into a copy of KQ. And now you color this lexicograph product, the lexicograph product of this graph. But if I color all the copy of each copy of KQ, all the vertices of that copy by same color, then I call this such a map simple. Okay? Simple. So if it's a simple, then this color does not depend on the second coordinate. So I just simply write this one as phi v. Okay? So use phi v to denote this color. Just determined by the vertex in G. Does not depend on the second coordinate. Okay. So another observation is that if both phi cosine are simple, then when they are adjacent, So if they are adjacent, phi is adjacent to cosine if and only if for every age u adjacent to v in G, this is in G. Okay. Phi u is different from cosine v. And also phi u is different from cosine u. So the first one is because u and v are adjacent, you put the second coordinate in, they're still adjacent. Right? So the adjacent vertices get the same colors. That's the definition of adjacency in exponential graph. For the second one is that because their I is different from j, and then ui is adjacent to uj, and this is, you're going to give this color phi u, you're going to this going to this going to give this color cosine u, so they have to be adjacent. They're adjacent in the next cooperative product. But in this way, if we look at phi as maps of the coloring of the vertex of G, we forget about the second coordinate. What does this mean? This means, say phi u is different from cosine u. This means that you can think of u as a loop there. If you have a loop there, there's a loop in the vertex U, then that is an edge. So then you go back to the definition of exponential graph. So you should have this requirement. So this means that the subgraph of KCGKQ induced by simple maps is isomorphic to this graph, to KC G naught, and G naught is just by adding a loop to each vertex, and G naught add a loop to each vertex of G. So G naught is to add a loop to each vertex of G, right? To each V belongs to G. So we'll think of KC G naught as a subgraph of KC G in this sense. We'll think of a map, say a map sending current vertices of G as a map in this graph. That means it's a simple map in this graph. So we think of this as a subgraph. It's an induced subgraph of this graph. Okay. So actually, what are we going to do? So let's look at this graph. So what are the sides of this graph? So we say P is about, the number of vertices in G is about 200. It is about 200. Then you get Q. Q is very big. It's about 2 to the 200. And C is also of the same order. C is even bigger, but it's also close to 200. Okay. So if you look at KC G naught, that means every vertex of you assign every vertex of G a color from C. So each vertex C choices. So the vertices is about on this side, which is C. C is 2 to the 200. And then how many vertices there? 200 vertices. So it's a huge graph. But what is this graph? This graph, how many vertices are here? How many vertices are here? G, K, Q. It's again, C is 2 to the 200. There are that many colors. And how many vertices there? Again, it's 2 to the 200. So you have that many vertices, and each has that many choices. So that's this big. So this is a huge number, but compared to this one, it's very small. It's very small. So let's draw this picture. So we're going to show the whole graph. This is the exponential graph, KC, GKQ. We're going to show this graph is not C-curable, but we're going to actually concentrate on this graph. It's a very small part of this whole graph. We'll concentrate on this graph and a little bit more. We're going to show this graph is not C-curable. So we're using only a small part of this graph, and then it's already not C-curable. Okay, so that is what we need to do. Okay, so again, another definition. For V is a vertex of G, and C is a color. B is a color. B is a color here. where that I, V, B be those simple maps such that the color of this map is equal to phi V and equals B. So this is the definition of IVB. So it's a subset. It's a subset of simple maps. Now, for every simple map, say for any simple map phi. Okay. Now, what is the color of this map? It is in the image, right? It is in the image of phi. So that means this is equal to phi V for some V, and you can see that the color, we name the color B. Then this means that phi belongs to IVB. So every simple map belongs to some of such set. Okay? So that means if you look at all these simple maps, okay, which is equal to the union of this set of such sets. Okay? So this V is chosen all the vertices of G, and B is chosen from all the colored set. And this union is not destroyed. They may overlap. Because there's a map belongs to many of these sets. Anyway, so let's have a look at the average size of this set. The average size. Of this set. What is that? This is going to be greater or equal how many maps are here? The number of maps is you have P vertices here, so it's P to the power C to the power P. So each have P vertices, you have C choices, that's C to the power P. And how many choices, how many sets here? You have P choices for this, C choice for this, so it's P times C. So this is C to the P minus 1 divided by P. That's about the average size. Actually, the average size is bigger than that. So this is that big. Okay. Then we define we define this is big. We say IVB is large. It's large if it contains this many. It contains this many vertices. That is 2p c to the p minus 2. So if it's this big, then we say it's large. But you have to compare with the average size. Say this 2pc p minus 2 is much smaller than the average size. The average size is p or c to the p minus 1. This is because this you multiply as 2p squared is much less than c. Much less than c. But c is 200 something. Now this is just P is just 200. So the average. So intuitively, this is just intuitive. This is the definition. This is intuitively, most of these sets, most of those sets should be large because this is much less than the average. Then we have this lemma. Again, this lemma looks quite natural then. This intuition. The lemma says make this vertex B such that you look at this set, you look at those B such that I, V, B is large, every V is large. Okay. look at this set. How many V's make this large? And this is greater than half of, more than half colors, more than half of those B for which this is large. Okay. You can find such a. Okay, so intuitively this is true, but we need to prove. I'll just prove it. Okay. So assume this is not true. Assume this number is not true. Assume not true. Okay. Then for V belongs to Vg, that without SV, those colors B, such that IVV is small. Okay. So SV are those colors which makes this small. Because we assume that the lemma is not true, which means that small means not large. Then for every V, this SV is at least CL to at least half of the colors make this set small. Okay, we define a set of simple maps. This is the simple maps such that for every V, phi V, it belongs to SV. So this is a subset of simple maps. For each V, if I V, it belongs to SV in this set. Then you look at this size of this set. So this is for each V, there are this many choices for the possible color of V. And you take the product, that's all the possible maps in L. And we know this is more than at least half C, so this is greater than half C times P. On the other hand, if phi belongs to L and phi is in IV B or some V and B, then this must be small. This is because phi V equals B. Phi V equals B. And this V by definition is chosen from SV, and therefore it is small by definition. This is small. So this implies that this set is contained in the union of those IVB. And this IVB, what are the union ranges of? So it ranges of all the small things, small ones. Ranges of the small ones. But then what is the size of the small ones? So because it's small by definition, so the small ones have size, what is small ones? The small ones size 2 to the P, 2 to the P times C to the P minus 2. So that is small means less than that. So each one is less than that. And how many choices of this V and B? You have P choices for V and C choices for B. So altogether is this big. But we know that this is great or equal to c over 2 times to the power of p. So we get this inequality. This implies that if you have cp, this is cp to the p to the power c to the power p minus 1. And so this means that c is less or equal to 2 to the p times this 2, that's 2 to the p plus 1, and times p squared. But this is so this is less or equal to what is q. This is q is greater or equal to 2 to the p minus 1 times p squared. Right? So this is less or equal to 4q. And 4q is less than 4q plus 2, which is c. That's a contradiction. C is less than c, so it's a contradiction. So we have proved this law. So what do we prove? We prove that there exists a v. So there exists a v, so we can fix a v, such that this set B, that IVB is large, FVB large. This set is more than half C. So this is. So then we can fix it. We can find such a vertex. So let's fix this vertex. Then I'm going to define another family of maps. So for T belongs to 2q plus 1 up to 4q plus 2. We define the map mu t in this exponential graph. This is not a simple mu t is not a simple map. It's defined as follows. It's defined. So mu t, you take a vertex in this next scopial product. So x is a vertex of G and I is a number in Q. So what is the color? It's a color. So mu t colors every vertex here by color from C. So it's colored by color I if the distance between V and X is either 0 or 2, and it's Q plus I if the distance equals to 1 and it's T. Otherwise, that is the distance V and X is greater or equal to 3. So that's a definition of mu t. So t we have 2q plus 1, 2q plus 2 up to 4q plus 2q plus 2 such maps here. Right. Okay, so first we show that this maps are pairwise adjacent. Let's write this alone. Okay. If t is not t prime, then this implies that mu t is adjacent to mu t prime. This is adjacent in the exponential graph. Okay, we'll prove this. Assume this is not true. Assume that mu t is not adjacent to mu t prime. Why is not adjacent? Not adjacent by definition. This means that there exists an edge xi adjacent to yj. This is in this GQ in this next scope of product of these two graphs, such that mu t xi is equal to mu t prime yj. Okay, so this is the by definition. This is why it is not adjacent. Now, okay, let's name this color. Let's name this color beta. So this color is beta. Then, by definition, what is mu txi? Mu txi is either I, q plus I, or t. Okay. So then this means that beta belongs to either I or q plus I or t. And what is yj? Yj is either j, q plus j, or t prime. So therefore, it is in the intersection. It is in the intersection of these t prime. Now, these numbers, I is at most q. So this 2 is 2q, at most 2q. And t is bigger than 2q. T prime is also bigger than 2q. The intersection does not contain anything. So t and t prime is not in the intersection. Okay. So this, if I and j, they are if I is different from j, then the intersection is empty. Right? So I has to be equal to j. I has to be equal to j. If I is equal to j and this is adjacent, then x has to be adjacent to y. Okay. Cannot be the same. So x has to be adjacent to y. In G, this is adjacent in G. Okay. Not in the. So x cannot be the same as y. Okay, so and beta is either I or q plus I. Okay. So let's consider the case. So if beta equals I, then why is I? Why do you have colored I? You colored I because you color xi by I, it has to be Vx is 0 or 2, the distance. So this means that distance of xv is 0 or 2. And similarly, when we color this by I, that distance between y and j, y and vi is also 0 or 2. Okay. So this adjacency is in G. Not in G naught, G. Okay, this is a contradiction because you have V here, and x is either V itself with distance 2, so this is x poses, and y is also distance 2 or V itself, but xy has to be adjacent. Okay. So this implies that you have a triangle or a C5 is a subset of G. This is a contradiction because G has girth 6. Right? There's no such thing. So beta is not I. Now, if beta is, I erase this definition. Should have saved this, but saved a little bit. So if beta equals q plus I, then what happens? Then you look at the definition. The definition, I just erased it. Then that means dgxv equals 1, and this is also dgy. dgyv equals 1. That's why they can send it to q plus I. This is again a contradiction. This implies that there is a triangle contained in G. This is not true. It's a contradiction. Okay. So we have proved this lemma. The lemma says that this mu t, they are pairwise. This mu t belongs to 2q plus 1 up to 4q plus 2. This is pairwise adjacent. adjacent. So this is a clique, induce a clique. This clique has 2Q plus 2 vertices. Right? So it has to be colored by distinct colors. So therefore there exists a T such that you look at the color of the mu T. It is not in this set. It cannot be all colored by this 2Q colors. You need 2Q plus 2 colors for this set. So they cannot all be colored by this. But it has to be in the image, right? But this has to be in the image. Has to be in the image of mu T. But the image is equal to this 1, 2, 2Q and T. It's either I, Q plus I, they are here, and the T. So therefore this phi ut equals T. So we can find a T from here that the color of ut is T. Okay, now I choose I choose the color B, which is not in here, not 1, not 2, not 2Q, and not T. So T is this color, this T, this T. We choose a B, which is not this 2Q plus 1 colors, such that IVB is large. IVB is large. We can find such a B because there are more than half C of those B. This is large. So this is only half of C. Okay. The more than half C that is large. So there is such a color B. Then we construct another map. We define theta belongs to, this is a simple map now. It's a simple map as follows. Theta x, which is either T if the distance between B and X is greater or equal to 2, and equals B if the distance between B and X is equal to 1. So this defines a simple map. Every vertex is colored. Okay, then we claim that this theta is adjacent to mu T. Theta is adjacent to mu T. Okay, let's prove this now. Otherwise, if it's not adjacent means what? Means that there exists an edge, there exists xi adjacent to yj. This is in the next cobra product. So we think of this x is xi for any I, such that theta x is theta xi. That's because it does not depend on the second coordinate. Theta xi is equal to mu t yj. Say let's name the color. Say let's name the color beta. Okay, then let's name the color gamma because beta I used already. Still confusing. It's gamma. Okay, then gamma has to be So by definition is the image of the theta, right? So the image of theta is either t or b. The theta x is either t or b. So this gamma is either t or b. It's either t or b. And gamma has to be in the image of this one. And the intersection, the image of this one. That one is, the image of the other one is 1, 2, up to 2q and t. Right? So that is the only possibility again. And the intersection, this intersection is just t. Okay? There's only one intersection because b is not in here. It's only t in the intersection. Okay, now, so theta x equals t. Theta x equals t. This means that the distance between v and x is at least 2. I think I made a mistake here. T is 2, so okay, so it should this is wrong maybe. So this is b and this is t. Okay. So it's if it's bigger than 2, I should map to b. It's less than 2, then I have to t. So then this means that it's t. That means that the distance is less or equal to 1. And why do you map this to t? By definition, and this maps to t. So this mu t y j equals t. When do I do that? This only if this vy is greater or equal to 3. Right? That's how I map it to t. But then this means that x is not adjacent to 1. X is the distance 1 and that is distance 3. They cannot be adjacent. And therefore, this xi cannot be adjacent to yj, which is a contradiction. So mu theta, this proves the lemma. So theta and mu t are adjacent. And theta and mu t adjacent, therefore, so this finishes the proof of lemma, and therefore you look at phi theta, it should be in the image of theta, but it cannot be the color of mu t. And the mu t is colored by t. Right? So it cannot be t. It cannot be t, and this is the image is only b or t, so it cannot be t, it's b. So theta, phi theta equals b. So phi theta equals b. Okay, now phi theta equals b. Then let's prove another lemma. So we prove that for every phi which is in this set VP, there exists x which is not equal to v, such that phi x belongs to t or b. And we prove this one. So we assume this is not true. Okay? Assume that this is not true. For every x which is not equal to b, Now, since this the color of theta is B, so the color of phi, because phi is here, so it is B, right? The definition, this is phi is here, that means the color of phi is phi B equals B, so this is B. And this is also the color of theta, right? Because theta is colored by color B. So they're both colored by theta, sorry, this is equality, yeah? They're both colored by theta, and therefore they are not, phi is not adjacent to theta. If they are adjacent, they cannot be colored by the same color. Phi is not adjacent to theta, that means this means the existent age, xy belongs to the age of g, that phi x equals theta y. And theta y, the image of theta is either b or t, so this is either t or b, because theta y, theta is map everything to t or b. But we said every x not equal to b, if x is not t or b, and therefore this says x equals to b. X equal to b. Now x equal to b and phi y, and xy is an age of g. So so distance of Vy equals 1. Xy is an age of g. Sorry, I should, this is in a simpler map, so they are not adjacent, it's in here, it's not, yeah, it's not, so x could be the same as y, because they are in this, the loops include here. So this not equal to x, less or equal to x. But if it's less or equal to x, then what is the, by definition, what is theta y? Theta y. Theta y is t, right? That's the definition of theta. If it's less or equal to 1, then theta y equals t. But phi x, but phi x is phi b. Phi b is b. So it cannot. They are not equal. So this is not equal. That's a contradiction. So this finishes the proof of this lemma. Okay, now so we'll finish it soon. So hopefully not tomorrow. Okay, so for x not equal to v, we that jx, okay, those phi which belongs to I, V, B, and phi x is in B or T. Okay. And by that lemma, so every phi in this here belongs to some jx, right? This x, phi x belongs to T. So this I, V, B is contained in the union of jx, and x is chosen from V, G minus V. All those x does not belong to V. Okay, now how big is jx? Now what is the size of jx? So jx are the maps, simple maps, right? Simple maps. But the simple maps those there be known here. So phi v equals b. The color of v is fixed. Color of v is fixed. And the color of x is, there are two choices for x. Okay. So this is less or equal to 1, that's 1. There's one vertex, that's a v. The color is fixed, has to be b. And there's 2, that's the choice for x. It has two choices. And each of the other has c choices. Okay. Every other vertex of G has c choices. So that means c to the t minus 2. There are t minus 2 other vertices. And therefore, you look at this size, IVB, is less or equal to the summation of this, or how many are there? So there are p minus 1. Okay. So it's less for p minus 1 times this size, which is 2 to the c to the p minus 2. Okay, which is less than 2pc p minus 2. But IVB is large. IVB is large. It is large. What means large? Large means that it's bigger than that. IVB is at least 2pcp minus 2. So that is the contradiction. This finished the proof. This finished the proof. Okay. So that's the end of the proof.